Why is ice so slippery? Why do curlers sweep like mad and speed skaters fly across the rink with barely a whisper of friction? In this video, we're diving deep into the science behind winter's slickest mystery. By the end, you'll understand what makes ice slippery at the molecular level, what is the slipperiest temperature for ice, how pressure, speed, and temperature shape your glide, whether wet glass is slipperier than ice, and how this all plays out in curling, speed skating, figure skating, and hockey. For centuries, scientists thought ice was slippery because pressure or friction melted a thin layer of water. But modern research reveals a deeper truth. The surface of ice is chaotic. To understand why ice is slippery, we first need to understand the difference between solids and liquids at the molecular level. In a solid, like ice, water molecules are arranged in a highly ordered crystal lattice. Each molecule is locked into place, forming a rigid hexagonal structure. In a liquid, molecules move freely and randomly. The order breaks down and the substance flows. Now, let's zoom in on the surface of ice. The water molecules here are still part of the lattice, but they're more loosely bound than those deeper inside. When a foreign surface, like a shoe sole or skate blade, approaches, its molecules bring their own electric dipoles. These dipoles interact with the dipoles of the water molecules at the ice surface. To minimize the dipole-dipole interaction energy, the water molecules try to reorient themselves. But here's the catch. They're still part of the lattice. They can't fully rotate without disrupting the structure. This leads to dipole frustration, a science jargon for when competing forces prevent a system from settling into a stable, ordered state. The result? The surface layer becomes disordered, breaking out of its crystalline arrangement. This disorder creates a quasi-liquid layer, a thin film where molecules move more freely, even at temperatures well below freezing. The motion of the foreign surface, such as blade, adds dynamic displacement, enhancing the amorphization effect. And that's what makes ice slippery. Not pressure, not friction, but molecular chaos at the surface. Let's take a moment to break down the molecular forces at play. Here's a quick sidebar showing the types of dipoles and how they interact with ice. You'll see how permanent dipoles, induced dipoles, even in metals and non-polar materials, can disrupt the ice surface and create slipperiness. Feel free to pause here and explore the chart. So now we know that slipperiness isn't just about melting. It's molecular disorder driven by dipole interactions. But here's the twist. Ice isn't equally slippery at all temperatures. Let's explore the sweet spot where ice becomes its slickest self. Ice is most slippery around -7 degrees Celsius. At this temperature, surface molecules are mobile enough to form a lubricating layer, but the ice isn't melting yet. Go colder, and the ice becomes brittle. Go warmer, and it gets sticky. It's a delicate molecular dance. Temperature sets the stage, but it's not the whole story. When you step, skate, or slide, you're adding pressure and speed, two forces that reshape the ice beneath you. Let's see how they change the friction landscape in real time. Slipperiness isn't just about temperature. Pressure compresses the ice, reducing molecular mobility. Speed generates heat, softening the surface. Together, they create a constantly shifting friction landscape. Friction is dynamic, but how does ice compare to other slippery surfaces? Let's pit it against a classic contender, wet glass. Which one wins the slipperiness showdown? Is wet glass more slippery than ice? Nope. Wet glass has a thin water layer, but it lacks the molecular disorder of ice. Ice's surface molecules are loosely bound, creating a lubricating layer more effective than water alone. Turns out, ice is slipperier than wet glass, and athletes know it. Different sports fine-tune their ice to match performance needs. Let's break down how temperature varies across the rink, the track, and the sheet. Each winter sport tunes its ice for performance. Figure skating, -3 degrees Celsius to -1.6 degrees Celsius for toe picks and landings. Hockey, -5.5 degrees Celsius for fast puck movement. Speed skating, -6 degrees Celsius for ultra-smooth glide. And curling, -4.5 degrees Celsius for controlled stone movement. From figure skating to hockey, ice conditions are tailored for action. But one sport takes surface control to the next level, curling. Let's sweep into the science behind the stone. In curling, sweeping is strategic science. Pressure and speed from sweeping reduce friction by warming the ice. Technique affects how much the stone curls or travels, and broom materials and pattern, from carbon handles to synthetic pads, change everything.
Curling is all about finesse. Speed skating? It's pure velocity. Let's shift gears and explore the physics that help skaters fly. Speed skating is a physics playground. Long blades maximize contact. Clap skates allow heel lift for longer strides. Aerodynamic suits reduce drag. And the ice? Engineered to perfection at -5.5 degrees Celsius.
From blades to brooms, we've seen how science shapes every glide. So next time you slip on a sidewalk or cheer for your favorite skater, remember, it's not just frozen water. It's a finely tuned surface where physics, chemistry, and sport collide. This is the science behind being slippery when wet.